So today's class, we do have an associated homework with it. Looks like some of you are getting your videos still working. All right. Just waiting on the last of you getting your videos out. Great. Okay. So before we start, this is a big lesson. I want to move rapidly through this one because you've got a handout on how to do Bode plots, but historically I found that cadets struggle with these concepts. So the more that you see me introduce it and talk about it, I think the better it will be for you. But before we do, does anyone have questions about anything? Cool. So last time, this is actually an extension of what we did last time. Today, we're going to begin by giving a quick review of what we covered last time. I'll talk about what decibels are, and then I'll show you how to construct a Bode plot. So last time we talked about frequency responses. And we said the frequency response is another word for a transfer function, where we replace S with J omega. But unlike H of S, unlike what you did with Laplace transforms, that was when you took the transform of your input, you found the Laplace transform of the system, you multiplied them together, and then you took an inverse transform. We are not doing that with frequency responses. Instead, we're thinking of the transfer response, the transfer function here, as like a gain. A gain is an amplification. And in particular, it's a complex gain that has both a magnitude of its amplification and a phase shift. And as a quick example, we have this cosine of 6t that goes into our system. And let's say that our system, this is something slightly different than what we had last time, but looks like this. And so if we put in a cosine in, what do we have to get out of it? Jonathan?
A cosine?
It has to be a cosine. And the only difference is that this cosine, the frequency has to be the same. So the only two things that are going to be different are its magnitude and its phase. And we can figure out what that magnitude is by just evaluating finding the magnitude of the transfer function at that particular frequency. So since it's 6t in, we'll set omega to be 6. And in this particular case, it happens to be 1.1. To find the phase angle, we just find the phase of 10 over J6 plus 10, which for this particular case happens to be minus 12 degrees. And in general, if we think about the input as being a phasor, of course, the phasor of this particular example that I chose is what, Joe?
Zero? Or wait.
This particular one.
Sorry. The phasor of it is just 1.
That's right, just plain old 1. But in general, it might have a magnitude out here, and it might have a phase shift in here. So in general, we could consider it this complex phasor. And if we evaluate the transfer function at omega sub naught. So by saying it's sub naught, what I'm saying is that it's a specific number. We don't know what it is, as opposed to this omega, which could be anything. And if we evaluate our transfer function at the omega naught that corresponds to our input frequency, what we're going to get out is a, excuse me, we're going to actually just multiply them together. We're going to multiply our input phasor by our transfer function, evaluated that omega naught. So splitting it out, you see we've got our input here, and we have our gain. And so we are multiplying them, sort of like we did with Laplace transforms when we multiplied our x of s by our h of s. But realize that this is not x of s. This is not a Laplace transform. This is a phasor. And this is a phasor. There's no s's. There's only complex numbers. And this whole thing is our phasor output. So let me give one slightly more complicated example of that. You've got, say, a 12 cosine of 2t plus 6 degrees. And so excuse me, and we want to see what this transfer function does to it. So we convert it into a phasor. We're going to evaluate our phasor at omega equals 2, which turns out to be 0.1 at an angle of minus 10 degrees. And so what we get out is going to be our 12 angle 6 times 0.1 angle minus 10. And it's true, you can very quickly multiply the magnitudes. You can add the angles. And so you can find that the result is going to be 1.2 times cosine of 2t minus 4 degrees. But although that is the correct answer, I don't want you to lose sight of the power of what we just did, which is that we're multiplying this input by our system, which is our complex gain. So it's somewhat reminiscent of what we did back in circuits 2 when you've got inputs that are phasors. It's somewhat reminiscent of what we did when we talked about Laplace, when you multiply an input by a transfer function, but it's not either. This is something different than we've done before. You do not want to take the Laplace transform of 12 cosine 2t plus 6 degrees. Firstly, you can't. The transform in the tables is this times u of t. And secondly, if you take a look at that transform, it would be nuts. You'd have to convert this into two parts, a pure cosine and a pure sine. And the input x of s would be just horrendous. So questions on this? This is really our review of last class. Okay. What we're going to do this time is just an extension of what we began last time. It's answers the question of how does h omega, it's complex, right? So we could say it's magnitude and phase is sort of two different questions. Change with frequency. Because you can see from the way that we're showing it up here that we're multiplying this input phasor by a gain, that if this gain is 1 everywhere, it's not going to change the input anywhere. If the gain is 1 for low frequencies and 0 for high frequencies, it's going to keep the input the same for low frequencies, but cut it down to 0 for high frequencies. And the opposite is true too. If the gain is 0 for low frequencies, but 1 for high frequencies, then it will keep any high frequency signal, but kill any low frequency signal. It'll be a high pass filter. So it's nice to be able to graph this. And last class, I just showed you what it would be if we graphed everything using a linear axis, using linear axes. And this class, I'll teach you how to do it by hand really quickly. And the answer to this question, how to do it quickly by hand, is called a Bode plot. Even though it's spelt Bode, it's pronounced Bode. And I'll give you an example of a Bode plot. In this particular value, we can use Bode plots to either plot the phase or the magnitude of h of omega. Since h of omega is complex, it's a phasor representation of what the circuit gain is doing. And in this particular example, I'll show you what an h of omega's magnitude would look like for a low-pass filter. And it would look something like this. If it was in linear, it would look like that, where this is 1, and this is 0. And this is a linear graph. And that kind of intuitively makes sense. But instead, for a Bode plot, the way it's plotted, I'll just abbreviate that, low pass, LP. Is it's done with its vertical in decibels. And 0 dB means a gain of 1 in linear terms. If it makes the amplitude positive, more positive, if it grows the amplitude in linear terms, if it's greater than 1, in dB, it'll be positive. And if it cuts it down as it approaches 0, in dB, it'll be negative. And then, to make things a little bit more confusing, the omega we're going to plot on a semi-log scale. So we might plot 0.1 here, and 1 here, and 10 here, and 100 here, and 1,000 here. So we're going up by factors of 10. And if we plot what this filter does, this particular one up above as a Bode plot, it would look like this. And I just did that by sight, but I'll show you how to do this by the end of the class, how you can do it by sight and get an accurate filter that does all the math of this. Remember, this is a lot of math, right? This is what we're doing here is we're evaluating the magnitude of 10 over j omega plus 10. And that's pretty hard to do. But what I just did over here is that exact same thing, numerically accurate just by sight. And you'll get to do this by the end of the class. But before we do, I have to first talk about what the heck this dB thing is. So, Preston, where have you heard about dB before?
Sound.
Right. And you've often heard about its correct name is dB for sound pressure level, and for dB for sound pressure level 0, people think that that means no sound. Does anyone know what 0 dB sound is? Maybe one of our musicians. So dB is actually it's a ratio compared to some standard, because true complete silence is negative infinity dB. Instead, the 0 dB reference point is an arbitrary reference to what the lowest amplitude sound is that you can just barely hear. So apparently it was taken for some older guys who made up the standard, because you guys can probably hear down to about negative 10 dB. I'm limited to about 0 dB. And then noises get louder exponentially from there. Speaking might be, a normal speaking voice might be 60 dB. A loud lawnmower might be 80 dB. If you're standing a meter away from a jet engine, that's about 140 dB. So what dB does, so this is for sound, but dB in general measures a ratio of power relative to some reference value. And for circuits, we use it to measure the magnitude of the system gain. We don't use it to measure phase, only for the system gain. And that's because for a filter, we often care about very large ratiometric differences. So for a low-pass filter, it might pass a low frequency. Its linear amount might be about 1. Its amount at 10 kilohertz might be 0.0001. Its amount at 10 times higher frequency might be 0.00001. And we care about how many zeros there are. So we want to have some way, some exponential form to pull out the difference between a 0.001 and a 0.0001, and dB does that. Let me draw that graphically. So we have a system, and we're going to put it up to a variable frequency input. So here's our system, right? H of omega naught. And this omega naught is whatever we put into it. And what we get out is going to be some k times cosine of omega naught t plus some theta, where if we evaluate h at omega naught, that gives us exactly what our k is and what our theta is. So that's what we've already described. And you can measure k. And what we do for a Bode plot is we measure so this is the gain part. This is how much it increases our signal. And this is the phase difference. This is how much it moves our signal left, right. And we can measure that k in two ways, in either linear terms as k, or in decibels, which we'll call gain in dB. And I've talked enough about the intuition behind it. Let's talk about the math. Math is very fast, as it always is. You can convert things from this linear valuation k into dB by taking its log base 10 and multiplying it by 20. And that means mathematically you can recover your k by saying it's 10 raised to the gain in dB over 20. Let me give a couple of quick examples about that. So I'm going to have this whole page for that. So here's our linear gain on one side, and here's our gain in decibels on the other side. And there's a couple of these things that you need to know. But let me start off, I'll star them, the ones that you need to have memorized. A linear gain of 1, that doesn't change anything. What you get in is what you get out. Chow, what's the decibel equivalent of a linear gain of 1? So put in 1 into this, and what's log base 10 of 1?
0. So
that's right.
0.
That's right. So it's 0. And we measure that in units of decibels. So, John Argar, what would be a gain of times 10? And this is another one that you should just have memorized. A linear gain of 10 corresponds to what value in decibels? Put in
That's
10.
one.
I'm sorry?
Is that 1?
Yeah, log base 10 of 10 is 1. So what's its gain in decibels?
20?
That's right. Plus 20. And that's something you should just have memorized. Now, here's the stuff you don't need to have memorized. Charles, let's say we go up to 100, a gain of 100. What's that in dB?
Is that 200?
Nope. Put that 100 into our log base 10. What's log base 10 of 100? If I asked you what the log is of 100, what would you tell me?
Is 2.
2. So 2 times 20 is
40.
40. So though this has gone up by a factor of 10 and a factor of 10, these only go up by a factor of 20. And you can continue that game out to find out, say, what would it be of 10,000? So, Connor?
Would that be 100 times 20?
No.
Would be 80.
That's right. And so the way to think about it, you can put it in your calculator or do the math, but the way to think about it is that every times 10 adds 20 dB. So all we did is we went up by 2 factors of 10. So we go up by 2 factors of 20. Okay. The next one is, what would happen if we multiplied by 0.1? What do you think about that? Joe Lieber? So now no longer are we increasing our signal. Now we're cutting our signal down. We're attenuating it by a factor of 10.
So wouldn't that be -1? So negative 20 dB.
That's it. So for every factor of 10 you increase it, it goes up by 20. For every factor of 10 you decrease it, it goes down by 20 dB. And so obviously if you go down by more, if you go down to 100th bin, what would you have?
This will be in -40s.
Right. And so we've contracted this massive span from, say, 100th up to 10,000 down to just 120 dB. So it graphs really nicely. There are a couple of other things you need to know. Here's one to memorize. Times 2. The only way to figure that out is with your calculator, plugging it out there. And the crazy thing is that even though log base 10 of 2 you'd think would be something insane, when you multiply it by 20, it comes out to be almost exactly, not quite, but almost exactly plus 6 dB. It's 6.02, I think. Really close. And that's important because often we care about doubling the signal strength. But if you know that, then Dom, what would be the decibel gain of a system that cuts down a signal strength by 1/2?
Would it be -6?
You got it. That 6 is important, so I'm just going to highlight that one too. Okay. Now, we can do a lot with this. Like, for instance, here are just some mathematical tricks that you can start to play. Times 20 gain. Well, that's really the same thing as times 10 times 2. And since times 10 was 20 dB, and times 2 we just said was 6 dB, That means the whole thing of times 20 is equal to plus 26 dB. So you don't need to have your calculator for an awful lot of stuff. How about times 5? Phil, can you see how to figure out what a times 5 linear gain would be in dB without evaluating this thing in your calculator?
Times 10 multiplied by 1/2.
Right?
So it'd be 14.
That's it. So it'd be plus 20 minus 6, which is 14 dB. So you can quickly find out how to do a lot of these things just by inspection. There's one last one that you need to know. The square root of 2. And that's the same thing as 2 raised to the 1/2 power. So therefore, in dB, that would be the same thing as 6 times 1/2, which is 3. And actually, of all these things, the two most important ones is those and this one. This comes around all the time. The reason why the square root of 2 thing is so important is actually not because of the square root of 2, but because of this weird guy, 1 over the square root of 2. And that's so important because if you multiply the voltage by 1 over the square root of 2, that goes into a standard load like a 1 ohm resistor, then you also multiply the current by 1 over the square root of 2. And if you multiply the voltage by 1 over the square root of 2 and the current by 1 over the square root of 2, that means the power going through is the product, which is just 1/2. And so at that point, you're at the half power point of your filter. And if square root of 2 is 3, 1 over the square root of 2 is minus 3 dB. And you'll see that all over the place. By the way, this happens to be about that. Okay. So when your filter cuts down, you put in a 1 volt into a filter, and what comes out of the filter is 0.7071. That filter is at its minus 3 dB point, which means it's passing half of its power. And by convention, we say that's where its cutoff is. Okay, questions on this before we get into the real meat of the lesson? Bode plots. I've got notes on your canvas for how to handle Bode plots. This whole section is on dB. So I've got notes on your canvas for how to handle Bode plots. It's also really well done. Your books are really good for describing how to do Bode plots. Separately, I've distilled about 10 pages of explanation in your books down to just, down to just 2 pages of notes. But the only way to do this is just to practice. And this is why we've got a required homework on this. And this homework is going to be one you're going to sketch out yourself and drop off in the box for me to hand grade. So let's talk about this last part, the frequency response plots, which is really, remember, just either magnitude or phase versus omega. And there's 2 ways you can do those. One is by MATLAB, and the other one is using Bode plots by hand. Let's do the easy one first, by MATLAB. If you're going to do it by MATLAB, I'll think it's easiest with an example. Let's say you've got a system whose transfer function is 1 over s plus 10. And you want to plot its frequency response from omega ranging from 0.1 to 1,000 radians per second. And once you do this, if you prefer to do it for frequency because it's easier to intuitively think about what frequency is, it's the exact same plot, just multiply the numbers in the bottom by 2 pi, and now magically it's in terms of frequency in hertz. So the way to do this is to, from your MATLAB prompt, begin by creating your omega vector. And an easy way to do that is to start off at 0.1 and increment it by something tiny, let's say 0.01, and go on all the way up to 1,000. You'll definitely want semicolons after that because that'll be about, what, 100,000 points. And then let's specify what our h is. So it's 1 divided by j times your omega plus your 10. So that was given in our transfer function up here. And of course, that's in general going to be a complex value. So we can get our linear amount, k, by getting our absolute value, our magnitude of our h. And then we can convert things into decibels by saying that's 20 times, whoops, log 10 of k. And now we plot the horizontal axis on a log plot. So we're going to plot the x side on a semi-log x, omega dB, and that's it. And that's your Bode plot by MATLAB. Now, an even better way to space them, since we're going to do it on, another way to do it is you could say plot omega dB. You could say plot omega k. This would be a purely linear plot, both frequency and both in horizontal and vertical. But this is what we've done so far. This is the most, intuitive, but this is the most standard way of doing it. Plotting dB vertically, and then plotting logarithmically over here. That's kind of the standard. So now how could you possibly expect to do this by hand? And by hand, this is the true Bode plot. It has a couple of restrictions. Firstly, it requires all real poles and real zeros. MATLAB can handle any kind of system. It could handle something like s squared plus I have to think about this, 10s plus 100. So this thing has imaginary roots in the denominator, which means it has complex conjugate poles. And Bode plots can't handle that. But Bode plots can handle things like this with all real poles. This has a real pole at -10. And at this point, I'm going to refer you to the handout. So let me take a quick look at this handout for you. So here's this handout that I made for you. It's 3 pages. So I've got 2 pages on how to graph the Bode magnitude response, and 1 page on how to graph the Bode phase response. You are not responsible for knowing how to plot phase responses in this class. I want you to look it over just so you've seen it. But what I really care about is that you're able to plot the magnitude response. This is something that you'll definitely need to know how to do in grad school. The only way to get good at it, as I've said, is to do lots of examples. And I'm going to start you off with an example right now. Let's say we've got our transfer function that we've just described, this 1 over S10. Your first step is to write down all your poles and all your zeros. So that's pretty easy. The zeros come from the numerator, and there are none. There's no value of S that will make this numerator go to 0. Whereas your poles have 1 at S equals minus 10. If you were to plot the S-plane plot, it would look like that. So the second step is to identify where you're going to plot it. Now, if I don't tell you where to plot it, you're going to look at, forget the negatives. Everything should have negatives for poles, right? Look at your smallest pole or 0, your smallest number, that's magnitude. In this case, we're talking about 10. And start by plotting from 1/10 of that. So just omega, from 1/10 of that all the way up to 10 times that. And that will give you a good picture of what the Bode plot looks like. However, in this particular case, I'm telling you where to plot it. Whoops, I'm telling you where to plot it. And so just write that down someplace, that you're going to plot it between 0.1 is less than or equal to omega is less than or equal to 1,000. On a test, I'll always tell you where to plot it. So far, we have this, and we have this. Your third step is you're going to draw the omega axis. And you'll fill in a logarithmic way what your omegas are. Notice that you can never get down to 0 omega if you're on a log scale. And then you need to know where to start. So the rule on where to start is that you're going to try, you could find out exactly what where to start this at 0.1, omega equals 0.1, by plugging in j 0.1 for S and evaluating its magnitude. So we're going to be plotting here. It's the magnitude of H of omega. And you can find it out exactly. Let's do that. So where we begin, this is subpart A. We'll begin by evaluating H of omega equals 0.1. And to do that, that's going to be the magnitude of 1 over j 0.1 plus 10, which is the magnitude of 1, which is just 1 over the magnitude of j 0.1 plus 10. And instead of plugging, if it's some sort of crazy number, you have to plug it in your calculator. But who haven't I called on yet? Sabine, just tell me roughly, what is j times, what is this, the denominator? approximately?
10.
Yeah, exactly. This imaginary part is so small compared to the real part. That's just 10. The whole thing is going to be about 1/10. And so, Jonathan, what is that corresponding gain in decibels for 1/10?
-20.
Exactly. So we're going to start off here at -20 dB. So that's our first point. Now, if there are no poles or zeros at 0, this is not the fact that it has no zeros doesn't mean it has a 0 at 0. If it had a 0 at 0, it would look like that. So this particular example does not have a pole at 0, does not have zeros at 0. And if there are no poles or zeros at zeros, then the Bode plot starts off going horizontally. If that wasn't true, if there were zeros at 0, if there was a 0 out here, maybe the h of s looked like s over s plus 10. So now you have a 0 at 0. Then for every 0 at 0, it starts going up by 20 dB per decade. And if there was a pole at 0, maybe it looked instead like this. So this would give you a pole at 0. For every pole at 0, it starts by going down by 20 dB per decade. But since we have neither of those cases, we start off going straight across. And we go straight across until, I'm just going to start by marking where any special places are. When you take a look at all your zeros and all your poles, write down a little X for every pole at the corresponding magnitude of this number, and write down a little 0 at every 0 at the corresponding magnitude of this number. And when you write your Bode plot, you're going to go straight across until you hit that point. And if that point is a pole, you're going to go down. And if that point is a 0, you're going to go up. And how fast you're going to go up or down is 20 dB per decade. This is 1 decade. This is another decade. Any difference in times 10 of your frequency is 1 decade. You're going to go down by 20 dB per decade for every pole you hit. And since there are no other poles or zeros, it just goes on down forever. And now you can complete your graph. So at 100, this is 1 decade up. It's 20 dB down. If it started at -20 dB, now it's going to be at -40 dB. And at 1,000, if it was at -40, now it's going to be at -60 dB. And so just by inspection really fast, is this filter a high pass or a low pass filter? Preston?
Low pass.
Low pass. Even though it cuts down our low frequencies by 1/10, it cuts down our higher frequencies by even more. And it drops down pretty fast. So by the time we get to a 1 kilorad per input, 1 kilorad per second input, it's dropped it down to -60 dB, which you'll remember is 3 sets of -20. So it's 1/10 of 1/10 of 1/10. So it's dropped it down by -1,000 of its input.
Sir, is the slope always going to be positive or negative 20 decibels?
The slope will always be 0 or positive or negative multiples of 20 dB, depending upon how many poles or zeros you had there. So
if we had another pole, it would go down to -40 dB per decade.
That's right.
Okay.
What Joe is saying is if this would look like this, now you'd have 2 poles here at -10. And now it would start off the same way, but it'd go down even faster so that by the time it reached 100, it would be down at minus 60 dB. And if it hits a 0, it just does the opposite. For every 0 it hits, it goes up by 20. So let me give one example of that. Let me give a much more complicated example. Let's let h of s be equal to 100 times s plus 1, s plus 1000, all over s plus 100 squared. So we're going to start off by asking where its zeros and poles. John Arger, where are its zeros?
Its zeros would be at 0. Wait, oh, JK, -1
That's
or -1000.
That's right. And when you said, does it have a 0 at 0, what happens when you put 0 into h of s? What does it be? H of s become?
Well, the bottom would be 0, so it would.
Bottom goes to 0, so it blows up, so that's a pole. So as long as you're on, tell me where its poles are.
0 and -100.
That's right. And it's got 2 at -100. Maybe a clearer way to write that would be this way. Okay, so if you were to graph its pole 0 diagram, it would have a pole here, a pole here at -1, a pole way the heck out here at -1000, and then it would have 2 zeros at 100. So this is not a very 2-scale diagram, but relatively it's correct. Okay, so if we were asked to graph the frequency response graph of this, I would look through here and go at 1/10 the minimum absolute value and then 10 times the maximum. The minimum is 0. That's the problem. We can't come up with 0 on a log-log plot. So that's the only exception, that for 0, we're going to graph it between, for this thing, we have to ignore the 0 and graph it between absolute values of 1/10 the smallest. So we'll graph it between 0.1 and 10 times the largest, which is 10 times 1,000, which is 10,000.
I'm sorry, I missed something real quick.
Shoot.
When you put in the zeros, you put them in at 100?
Did I do that back? Oh gosh. Thank you. Thank you. Yeah, I don't know what I was thinking there. We have a 0 here, and we have a 0 here. And then we have poles here and 2 poles here at -100. Thank you very much. I appreciate that, Phil. Okay, better? I'm still got my coffee. Okay, now let's begin. We have to figure out where we're going to start graphing this thing. Well, firstly, we're going to have to set up our megas. So that's going to be 0.1, 1, 10, 100, 1,000, 10,000. Some of you might find it easier to graph it by powers. In many ways, that is easier. And then we'll start to graph. So we firstly need to figure out what we're beginning with. What is h to start with? We need to find out what is h at our smallest value, which is going to be omega equals 0.1. And I need to tell you if I'm graphing its magnitude or its phase angle, and I'm going to be graphing its magnitude. So to graph its magnitude, we throw that in there, we're going to get 100 times j 0.1 plus 1 times j 0.1 plus 1,000 over j 0.1 times itself times j 0.1 plus 100 squared. We want to find its magnitude. So that looks kind of hard at first, but we can see we can separate our magnitudes out into the magnitude of each part, and the magnitude of 100 is 100. And the magnitude of j 0.1 plus 1, because these two pieces are separated by at least a decade, by at least a factor of 10, the magnitude of this is pretty close to exactly 1. Magnitude of this is going to be pretty close to exactly 1,000. What is the magnitude of j times 0.1? Joe, Lieber? The magnitude of this part.
Would that be 0.1?
That's right. And then the magnitude of this, kind of using the same reasoning, is going to be 100 squared. So now we can simplify a little bit. I can cast out, let's see, we got, this is 100 squared, so that's a total of 4 zeros. That's 1, 2, 3, 4. And so that gives me just 10 over 1/10, which is 100. And in decibels, what's that been?
So you said
40.
so that would be 10,000.
What is 100 times 100 gain in 40 decibels?
So it's
Do you remember how to compute that from back here?
so like 20. Oh my bad. So
That's
it's 20 times log of 100. So that would be 40.
That's right. And that's correct. And the way that I think about it is that it's times 10 times 10. So it's 2 sets of 20 up from 0. So we're going to start graphing this at 40 dB. All right. And the next question is, does it go straight across or up or down? Does it have any, if it has no poles or zeros at zeros, it goes straight. But in general, every time you see a 0, it wants to pull it up. And every time you see a pole, it wants to pull it down. So Phil, where's it going?
So I was taking notes on that last little bit. I think it's going to go down.
That's right. Because we have a 0 at 0, and that 0 at 0 is a pole. I'm sorry. Because we have a pole at 0, we have a root at 0, and that root is a pole. It's going to start by going down. It's going to go down, since there's only one pole at 0, it's going to go down by 40 dB. So after 1 decade, it'll be down by, since there's only one pole at 0, it'll go down by minus 20 dB per decade. So after 1 decade, it'll be at 20 dB. And let's see, is there anything that we're hitting at 1? Yeah, we're hitting this guy at 1.
Hey, sir, I have a question.
Shoot.
Just real quick. I'm sorry. You might have explained this before.
Yeah.
Where'd you get the actual ratio to drop by 20 again?
That's the rule, is that for every pole it hits, it's going to go down by 20 dB per decade. For every 0 it hits, it goes up by 20 dB per decade.
Where'd that 20 come from? Was that from earlier as you go through the log scale that it changes by 20? Is that what that comes from, or?
It comes from the rule that Bode discovered.
Okay, sounds good. I'll just remember that.
Yeah. If you're really kind of curious, it comes because if we evaluate, it's a good question. If you've got a transfer function that looks like this, say. So it's h of omega will look like j omega plus 10. And if we want to graph its magnitude, that's its magnitude. And for when we increase our omega, if our omega is already rather large, as we increase omega by a factor of 10, you can see that this will also increase by a factor of 10, the magnitude of the whole thing. If omega is already big, if omega is already 1,000, say, increasing it to 10,000, you can ignore the 10, and that will increase the magnitude of the whole thing by a factor of 10, which will drop this whole thing by a factor of 10. And dropping it by a factor of 10 corresponds to a change in 20 dB. And if we had this squared, then this would be squared. And now it would drop it not by 20 dB, but by 40 dB. So that's where it comes from. But it's easier just to memorize the rule that for every 0 it hits, it's going to go up by 20. And for every pole it hits, it's going to go down by 20 dB per decade. And if this was the only, let's see, and if our entire system just looked like this with nothing else, this would continue to go down at that rate. But it doesn't. Instead, what happens next? It's going to encounter a 0. We always look at the magnitudes here, so it's going to encounter a 0 here, and it's going to encounter 2 poles here, and it's going to encounter another 0 here. So it goes down until it hits the 0, and then bin. Does it tend to continue? Does this 0 want to make it continue to go down, or go down even harder, or start to go up?
It will start to go up.
Start to go up. But because it's already going down by 20 dB per decade, this 0 here is going to just make it flatten out at 20 dB per decade. And it's going to continue to be flat at a gain of 20 dB, at a gain of positive 20 dB, until we hit these 2 poles here. And what will those 2 poles make it do, Phil?
Is that gonna drop it?
It's going to make it drop. By how much?
By 40 dB, right? Because there's 2 of them.
By 40 dB. And since it was going at 0, now it's going to drop by 40 dB. Now, if these 2 poles hit back here, since it was already going at minus 20 dB, now it'd be dropping at negative 60 dB. But since it was flat, it just drops at negative 40 dB until we hit the 0. And then what's the 0 going to make it do, Sabine?
Will it make it drop only by negative 20 dB per second?
That's it. It'll even it out to minus 20. And since it hits no more poles or zeros, it'll continue on that way forever. So that is all that a Bode plot is. The rules for doing the phase, really similar. The only difference is that the phase drops it by exactly negative 90 degrees for every pole, or raises it by positive 90 dB for every 0. And unlike the poles and zeros effect on the magnitude, where these effects continue on forever and ever, for angle measurements, it starts at 1/10 before your pole and it continues 10 times beyond your pole or 0, as long as it drops it by a total of negative 90 or positive 90. So I'll let you read about that in the student hand guide. I do want you to be just vaguely familiar with how things work for phase, but I'm not going to ask you to do it on a test or I don't think I have any homework problems. Excuse me, on it either.
Sir, I have a
Okay.
quick question.
Shoot.
So a couple quick questions. One, if our zeros and poles are like negative 1,000, negative 1, and then 0, negative 100, negative 100, how come those wouldn't be represented on that W axis? Those are like positive numbers. Why wouldn't they be negative? So like
Yeah, it's just
your zeros would be like that 0 at 1,000 would be negative 1,000.
Well, it just so happens that if we had, we only care about the magnitudes.
Oh,
If we had a
okay.
0 out here at 1, then that would be like having double zeros at 1, and now it'd actually be going up by 20 dB if we had that. Let me just do that in a different color so it's clear. So if we had this at +1, then we'd have another 0 at +1. And now we'd hit 2 zeros here, and now it'd be starting to go up at +20 dB per decade. You never have to worry about poles being over here and poles being over here. And why is that? Why will that never happen?
Because it would just go to infinity and wouldn't be good.
Right, because if you have any poles in the right half plane, that would correspond, that would mean your system is not bibostable, and if you give it the slightest input, it'll just go off to infinity, positive or negative, and it's not a system of interest because it's unstable. Remember, this corresponds to an H of S that looks like something over S minus 10, which corresponds to an impulse function that has a e to the positive 10t. And so this system is fundamentally unstable.
Sir, I have
Question,
a question about starting the function. So I understand where you get the very beginning, you set up 4 decibels, that's fine.
Yeah.
And the reason we go down though is because the closest pole or 0 is at 1, right? And that's because it's
No, the reason why we go down from here is because we have already hit a pole at 0. Where is that pole? It's way out there at negative infinity. We can't graph it, but we already hit that pole.
So let's say we didn't have that pole didn't exist. Would it start flat? What would
That's
it
right.
start?
That's right.
Sir, I have a question as well. So where you had that 0 at 1, the magnitude of 1, and you're going down, you're starting by going down at negative 20 dB per decade. And then what that 0 would cause it to pull up at positive 20. So it's flat because it's pulling down and up at the same time until it reaches the next pole.
That's right. That's right. It starts off going down because of this pole at 0. Remember, where along this axis is omega equals 0 way over here. So it already hit this pole. So it's already going down 20 dB per decade because of this pole. And then what does it even off at this point because of that 0 up here, which tends to make it want to move up by 20 dB per decade, which cancels down its current minus 20 dB. Just like what happened out here at 1,000, it reached a single 0, which makes it want to go up by 20 dB per decade, but it was already going down by negative 40 dB per decade. So now it's going to go down just by negative 20 dB per decade. Does that answer your question?
Yes, sir.
So let's go back to the very first problem we did in the
Can I
beginning.
ask one more question?
Yeah, sure.
The reason we started at 0.1 was because that's the lowest value. Is that correct that we can calculate? Is that why we started there?
That's right. We took a look at at the magnitudes of all of our poles and zeros. We said the magnitudes of all of them are 0, 1, 100, and 1,000. That's where these are the frequencies at which something interesting is happening. And we can't graph 0 on our semi-log plot. It doesn't exist. It's off to the left at negative infinity. So the only ones that we can actually graph, that we can actually see, are in this range. And that's also, and so we're going to, since interesting things happen at these points, we want to start graphing at 0.1. That's a 10th. So we can clearly pick up what this thing is at 1. And we want to continue graphing to 10K. So it's 10 times bigger than the largest one. So we can clearly see the effect of this guy.
Thank you, sir.
Sure. Any others? Let's go back to our very first thing we did to start out the lesson. We talked about this low pass filter over here. And so just by looking at it, when I went to compute its Bode response, I put in my mind's eye this 0.1. Now I knew there's no zeros or poles anywhere here. There's no zeros or poles at 0 anywhere here. It has no zeros. Its only pole is at -10. And so I know it's going to start off flat. And so though I could have put in this J 0.1 in here and tried to work it out by mind, it's even easier than that. Since I know it's flat, instead of putting in J 0.1, I'm just going to put in even further to the left, J. If it's flat, it should be the same at J times 0.01, J 0.0001. I'm just going to put in 0. If it's flat, it's got to be flat all the way out. So I put in 0, and I can just see that's just 10 over 10, which is 1, and a gain in decibels of 1 is 0. So that's how I knew I started out at 0 dB. And then I could see that the only interesting thing going on here is that my pole at S equals -10. So something is going on here at this 10 point. And it's just one pole, so it's going to go down by -20 dB per decade. And that means at a 0.10 higher, it's got to be 20 dB lower. And that's how I was able just to graph that just by inspection, and how you can too, using Bode plots. So when I was an undergraduate, I said, why are we wasting all this time on Bode plots when, wham, MATLAB does it. MATLAB does it instantly, and MATLAB does it for even non-real poles and non-real zeros. If you have poles and zeros out here at these complex conjugate points, when you're far beyond on either side of this pole, it's as if there was a double pole here. But when you're in the middle of it, it creates this weird peaky thing around it that you can't graph exactly and is painful, which is why we say Bode's really only work for real poles and zeros along the number line. If MATLAB doesn't have that restriction, why are we spending all of our time on doing Bode's? Why not just do MATLAB? And the answer is that firstly, even if you are doing it with MATLAB, everything's always plotted along these kind of plots with log space frequency and magnitude in decibels. So it's important to get used to just to seeing what it looks like. But secondly, there's an awful lot of intuition that comes from being able to do it by hand. If you see that MATLAB throws up a diagram that looks like this, and we say, hey, we want the same shape, but we'd like to raise this section here by say 20 dB. If there's some design criterion that says we would like it to look instead like this, well, knowing how MATLAB does it alone doesn't tell you how to do that. But being able to calculate it by hand lets you say, hey, all I need to do is just move this zero rather, to the left by a factor of 10. All I need to do is replace this s plus 1 with an s plus 1/10, and voila, now I've got my answer. And that kind of intuition, that kind of seeing how you change your circuit to meet a changing design criterion doesn't come from just being able to analyze things using MATLAB blindly. Anything else? And then I will let you go. Work all of those collaborative problems. Work through the problems on the handout that I've given you, and then the homework will be nice and clean, I promise. I'll see you next class. If you want to stay on for questions, you're welcome to.
Thank you, sir.
Thank you, sir.
Is the homework due before class in your folder?
Say it again, Phil.
The homework is due, is it this Friday in your folder?
The homework is due. No, it's due before next class, which will be before Tuesday.
Okay, all right. Thank
Yeah,
you, sir.
if you want to take a quick look, it's, give me a second. So if you want to give it a quick look, it's this is the homework, and yeah, and although I didn't say it, I do need to say that it's due before the beginning of next class. I'll make that change now.
Thank you, sir.
You bet.
So that says that it needs to be printed. Can we just like draw it out on paper, or do we actually need to print that?
As long as you give me a printout of your answers, I don't care what technology you use.
Sir, I had a question regarding your website and the MATLAB. I was trying to find what you were referring to in order to download it onto my computer, but I was unable to. I'm on your website right now, and I was just wondering where exactly to find that that link.
Okay. So do you see what I've got on my screen? This is for module 1. This is our very first day, lecture 01.
Yes, sir. Oh, it's on Canvas. It's not on your website.
Yes. Did I say website? I'm sorry. I meant Canvas.
Oh, okay.
Yeah, I've moved everything off I'm moving everything off my own private website onto Canvas. So if you go to the very first lecture, it's on the Get MATLAB here.
Modules 1. Oh, okay, perfect. Thank you.
You bet.
And then for, I guess, so I'm assuming that we're going to be taking transfer functions of circuits and then analyzing the Bode plots of those transfer functions, right?
That's right.
Okay.
And then from that, you'll be able to instantly see, is the circuit a low pass filter, a high pass filter, a band pass filter? What is it doing?
Okay. And then my other question is, so for the test, I put in probably 15 rough hours of studying, and the grade that my performance on the test was not what I was not happy with it.
Yeah.
And
yeah.
so I was just wanted to talk to you about what I could be doing differently in order to get into that higher
Sure.
threshold of
First
score.
answer is I'm being kind of quick because Jonathan's also got a question, and then I've got another test, class right after this. But the answers are, firstly, are you doing all the collaborative problems for every lesson?
Yes, sir, I am.
And are you doing them entirely alone?
Yes, sir.
And are you doing
When I don't understand it, I seek help, or I look at I seek help from the other, like Dom or Philip or people that.
Yeah. Okay. So if you can do a collaborative problem on your own, then you know that material and you don't need to waste more time on it, because I know everyone's time is really at a premium here. But if you can't do the collaborative problem entirely on your own, and you need to look at either the solutions from a classmate like Dom, or you need to stick around and ask me questions about it, or you need to take a look at the solution, then that means that although you'll feel warm and fuzzy about understanding the material, you absolutely do not know it. It seems counterintuitive, but if anyone helps you with it, or if you get any information from anyone else other than yourself, it means you do not understand it and you will not be able to do it on a test. So that's why the collaborative problems are there. If you can't get it from the collaborative problem entirely alone, switch to the textbook and find a similar problem from the textbook and work it. And be able to work it entirely alone. And continue to do that. If you can't do it alone, get help from the textbook. It's a work problem, and then realize you still don't know it, then get additional problems. If you use up all the textbook problems, I've got on my shelf in my classroom a whole bunch of textbooks with solved problems. Go through those until eventually you can solve a problem like the collaborative problem with no extra help. But that's the trick, is at the moment you need help from me, it's all over. You've lost that learning, that opportunity to learn. which I know is really counterintuitive, right? Because when I explain something, it's like, okay, now I understand it. Now I get it. You feel good. But the truth is that you absolutely don't know it. And that's why I try to, that's why I'll explain things first, but then I give you stuff to work independently. Or if you ask me help for things, I'll give you just a very small little hint rather than telling you everything. Because if I tell you everything, I've robbed you of that chance to learn. So that's the biggest thing. And to have that learning opportunity happen, not when you're preparing for the exam. You shouldn't be spending 15 hours preparing for an exam. All that time should be done in the process of learning it, because your brain will consolidate that information. It actually happens while you dream. You myelinate connections inside your brain while you dream, and it can take actually weeks to form. So it's why if you wait until a week before an exam and you spend 15 hours, it'll work great for mostly recall kinds of things like history, but it will work very poorly for electrical engineering. The way to do it is spend that time as you go, be able to do the collaborative problems as you go, and then when you take a look at when the exam comes around, you'll have made all kinds of neat connections from weeks and weeks before. Sounds counterintuitive. Working these problems alone will also, instead of making you feel confident, it'll make you feel anti-confident. It'll make you feel very weak and insecure. But that is the right way to feel. Working things out in groups or getting help from any other source, it's really weird. It makes you feel more secure, but it actually will give you a much worse grade. Does that help at all?
Yes, sir, it does. I really appreciate your time. I'm going to let Jonathan ask his questions and let you go on with your day. I really appreciate it, sir. Thank you.
Yeah, you bet. I think Jonathan's questions were actually kind of similar to yours.
Yeah, no, I just wanted to thank you for all your help yesterday. I figured out most of the stuff, and I'm going to go over the one thing from number 4 over the weekend. I got really caught up doing some stuff yesterday. So.
Yeah, take your time. Yeah, take your time, but you're right. Now is the time to do it, right after the test, not before the next one. And when you do that, I can't tell you how, but when you sleep, stuff happens. And when you come back, you'll see connections in other stuff that we cover that you wouldn't have seen otherwise.
Yeah, I realized that number 1 was just so easy. When I looked back at it, I was like, oh my gosh, how did I mess that up?
Yes, and the more that no, I know exactly how you did it. It's because we had a homework problem almost exactly like it. And I bet on that homework problem you got help. Or you got help on it. And therefore the learning opportunity for that was completely lost. And then when I showed you what the answer was, and you're like, oh yeah, that's so obvious. Again, that learning opportunity was lost. So, and it's so, what's the word? It's frustrating, right? When you see what the right answer is and it's so easy and you know you've seen things like that before, but it just goes to show how what helps us learn the most effectively is completely non-obvious. It's not just you. Every electrical engineering, every engineering student grapples with the same thing, but it's only engineering students and math students. Students who are, say, medical doctors, they never hit this. You explain something once, it's a very superficial understanding, it's just a fact recall, and that's all they need.
Yeah, thank you, sir.
Yeah, you bet. Take care.
Have a good one.
And